Okay, so let's look at the information that's given. We have the area under the curve of f of x, and then g of x. Notice that's different, but the bounds are the same for the first and the last. So I know the area under the curve from -2 to 7 of f of x dx is 13. And I know that the area under the curve from -2 to 3 of f of x is -5. And then I know that the area under the curve from -2 to 7 of a different function g is equal to 3. So what we're going to do is we're going to evaluate the first part. And I have to find the area under the curve of f from 3 to 7. Well, I know the full area from -2 to 7, and I know the area from -2 to 3. So I'm not saying you have to do this, but here's kind of the idea of this concept is what do we know? Well, I know that if I go from -2 to 7 of f of x, that can actually be split up as the integral from -2 to 3 of f of x dx. That's what this middle one says, from -2 to 3. And then we know that if I go from 3 to 7, that will complete the full distance from -2 to 7. So remember our properties. We go from -2 to 3 and then 3 to 7. And these two added together give me the full area. Now let's think of what we want, right? I want to find the area under the curve from 3 to 7. So I want to find this value right here. But I know the first one is 13. And so I'm just going to substitute. I'm going to replace that. This whole piece is 13. And then we know the area under the curve from -2 to 3 of f of x is -5. So then all I have to do is move that over to the other side. And by the way, if this was a multiple choice question and you could do all of this in your head, you don't have to show any work at all, right? You could just say, oh, well, okay, if the whole thing is 13 and I subtract a -5, so then in this case I have to move the 5 over, and that will give me 18 is the distance from 3 to 7. Okay, so the answer to this one is 18. And the reason why I showed all this work was just so you could see how the properties work, and that's part of what the video was. All right. Part B is almost the exact same thing as what we have here, except for we have a constant multiplier. And when we have a multiplier, there's something you can do. You can actually pull that multiplier out. It's the same way, it's the same properties basically as we had with derivatives. So if you remember all the properties, you can take the derivative and then times it by a constant, or you could times it first and then take the derivative, and this is the same way. I can take this pi and I can pull it on the outside, and then what that allows me to do is notice I now know exactly what -2 to 3 of f of x dx is. That was given. So the pi drops down, and then we multiply that by -5. And then my answer is -5 times pi. Okay? All right, I'm going to bring this stuff down here because I need these facts from above to do part C and part D. And part C is really quick. Part C is the property that says if you have two functions, g and f, and they're evaluated at the same bounds with either subtraction or addition, you can rewrite this as two separate integrals evaluated at the same bounds. So I'm going to take g of x from -2 to 7, and I'm going to subtract f of x from the same bounds. And the reason why we officially have to show or do this property is because my two given facts down here cannot be plugged in until I have exactly that. Right? So what is negative 2 to 7 of g of x? That's given right here. Negative 2 to 7 of the function g of x is equal to 3. And then we're going to subtract. What is f of x from negative 2 to 7? Well, here's negative 2 to 7. F of x is 13. So it's just substitution. And then we replace those, subtract, and we get the overall answer is negative 10. Okay, so it would be the same thing if this was addition. You can split those up using addition or subtraction. Now, part D is probably the one that gets a lot of kids confused, or they miss a very, very simple step, but it's tricky, so I maybe shouldn't use the word simple. Now notice, we actually have a couple properties mixed in. I have a 4, right? That's a multiplier. However, that 4 is not being multiplied by the 3, so I kind of have to do 2 steps in one here. My very first step is to use the property that we used in part C. I have two functions. I got 4 times f of x, and then I have 3. And both of them are being evaluated from the same bounds. Now, I'm going to use the luxury of my smart notebook file to do this. But what I'm going to do is going to write the first term with a dx with its integral, plus now I'm going to evaluate the second one with the same bounds. So notice that 3 is a function. Okay? So now, here's what I can do. I still have this multiplier. The multiplier does not belong to the 3. That's why I didn't put a 4 out here, or I didn't pull the 4 out right away. But now that I isolated this integral, this 4, if I can grab it, that 4 can actually scoot right out in front, kind of the same way that pi did, right? It's a multiplier, so I just pulled it out. But I couldn't pull it out until it was isolated because the 3 didn't have that multiplier. So now I get to use the fact that I know one of these as a fact, right? This right here, the integral from negative 2 to 3 of f of x dx is right here. Negative 2 to 3 of f of x is negative 5. So I don't have to evaluate that. I know what that answer is. I'm going to just replace it with 5. But I do not know this answer. This answer, I actually have to evaluate. It doesn't have a function, or it does, its function is 3. It doesn't have an f of x or a g of x. So I cannot replace this, which means now I have to do the antiderivative. And you had a quiz on Monday, and I'm just going to let you in on a small little note. So we're going to evaluate this. I have to take the antiderivative of 3. So I'm thinking, whose derivative gives me 3? Right? So I'm going to write the antiderivative. That's 3x. Now what I noticed, by the way, when you go check your quiz, some of you had took the antiderivative and then you wrote the integral symbol again. That's incorrect notation. It's poor notation. This symbol for integral means take the antiderivative. Once you have it, that symbol, the integral symbol, is no longer there. But we do have to still evaluate the bounds. So this line is kind of what the dx is. It's evaluating from the upper bound minus the lower bound. So now I'm going to take the antiderivative of 3x, and I'm going to plug in 3 first. And then I'm going to subtract the value 3x when we plug in negative 2. And this becomes 9 plus 6, which is 15. And if I simplify this piece, I get negative 20. And then just know that those have to be added together. My overall answer is -5. Okay. It takes a while to get used to that. If this is the first time you saw this, please go back and watch that video. Okay, really quick, do this in our calculator. But today, we're going to re-emphasize some of those properties of integrals that Mr. Waffler talked about. Officially, we're starting section 6.4. And we're going to spend 2 days in this. So today, and then Monday, Tuesday of next week. And then we're going to have a review day. And then on Friday of next week, you're going to be assigned, Thursday or Friday, you're going to be assigned the test for this unit, and it'll be due on the 15th, which is the Monday of President's Day, I believe. We don't have school, but it's due that day. So you can get it done Thursday, Friday, Saturday, Sunday, or Monday. Get it turned in. All right. Do not write this, but this is just a very quick overview of the integral properties that we've already introduced or Mr. Waffler talked about in the video on Wednesday. So the first one is remember what happens. And by the way, this was some of you, when you go back and look at your quiz, one of the problems, I can't remember what number, it was 9, 10, or 11. And it was find the area under the curve, but our bounds were switched. So notice, if I go from B to A, and then I switch the bounds, we have to compensate for that and put an opposite value out in front. And that was one of the problems on the quiz. The bounds were switched, and you had to find the area under the curve, but it was the opposite value. So just a little hint there. So we've talked about that one. We've also talked about if I go from A to A, well, that's the area under the curve, but if I go from A to A, which means I don't move in terms of my x's, it's a straight line. And the answer to the area under that curve is always 0. By the way, if you're like, oh, I really like this slide or I want it, it will be posted later today as soon as we get done with class. Okay, well, what about this one? If I have an integral from A to B and K is a constant, I could put C, K is the same thing. Well, if K is just a number, what does that mean? I can pull that constant multiplier out and deal with it later and then take the antiderivative. And the benefit to doing that, you might think, well, why would I want to do that? Is a lot of times when you multiply a function, it gets more confusing. It gets larger numbers or it can really make it not friendly. So if you pull it out and evaluate the integral first, and then whatever this answer is, you're going to multiply all of it by k. So we call that a constant multiplier. And by the way, Mr. Waffler went through this kind of graphically. I'm not going to do that here, but let's say, I'm not going to go crazy with this, but let's say that here's my value, this is my f of x, and if I go from A to B, we know that the area under the curve is represented by the integral. Well, what happens if I multiply that by k? K is a multiplier, so that's going to make this increase or decrease by a certain value. So it's actually going to double, triple, or cut it in half. It's going to give you more area or less, depending on if k is greater than a 1 or less than 1. Or if it's negative, it'll reflect the area down below. Okay, we've used this property in the warm-up. If I have the integral from a to b of f of x plus g of x, we can rewrite this integral and evaluate each one separately from the same bounds. So notice f of x from a to b, and then g of x from a to b as well. Okay? That's kind of like splitting a function up and finding the area under the curve of one and adding it to another. And you could do the same thing with subtraction as well. And that's all this one says is basically addition, subtraction. It doesn't matter. You can split them up and evaluate each one individually. Right? And we'll show you these all today. The one that we've talked about already is this is kind of like our area addition model. Let's say that I've got a function from a to b and then to c, and I've got a curve that looks like that. Okay? Well, they're saying that if I find the area under a curve from a to b, underneath the curve, that would look like this, right? And then I find the area under the curve from b to c, that would be this area. But they're saying if you add those together, well, isn't that the exact same thing as going from A to C, right? And the reason why is this is a continuous function, and it's just saying that the area under the curve can be split up or added together to get a larger area. So nothing crazy there, right? We've kind of already talked about a lot of those. This one is new, but I don't think you need to write it down. And I know Mr. Waffler doesn't talk about it. All it is, and it's kind of confusing, but look at right here. It says the area under the curve. Right? We know that this notation from A to B represents the area underneath the function. So if I had a graph, that would be all of this right here. From A to B, area under the curve. Well, notice how we have the integral symbol. It's kind of like sandwiched between. All it's saying is if we were to take the minimum function, the lowest value, so on my graph here, let's take the lowest value right here. And if I was to create a rectangle with this width and this height, it would look something like that. Right? And I can calculate that pretty quickly. Right? That's just length times width, and its area would be represented, oops, right there. Well, what if I did the same thing, but now I wanted to go from the maximum value? So if I take the maximum f of x, so the highest that the function goes, and I create a rectangle out of that, its width is b minus a, right? That's the width. And then the height is just whatever the highest f of x is. Well, that's width times length. That would give me this area right here. And notice, this is going to give me the highest possible area under the curve. The minimum will give me the lowest, and we know that the integral itself is somewhere in between there. It might be equal to the lowest or it might be equal to the highest, but it's not going to be lower than the low or higher than the high. All right. So what does that kind of tell us? And there's a second thing. If we have two functions, this is a separate concept. And it's kind of common sense. That's why we're not having you write these ones down. But let's say that I got f of x. And f of x is this function. And then I've got g of x here. And I want to go from a to b. If f of x is, oh, these two should be flipped around. So if f of x is greater, so if f of x is higher than g of x, for every value, then we know that the area underneath the curve of f of x, the area underneath the green curve, is going to be greater than the area underneath g of x. Right? Because f of x is always higher than g of x, so therefore the integral will be greater. And that's just kind of wrapping our heads around this kind of idea of a max and a min, high point, low point, area under the curve. So how are those properties going to come into play today? That's what we're going to see. I would like you to write this down. This could be very intimidating as a problem. If you saw it on a free response question, or a multiple choice part on the AP test. A lot of students kind of freeze because of this notation for a piecewise function. But if we have a really strong connection to the properties of the integrals that we just learned, this actually is a pretty friendly problem we can do without a calculator. So I'll give you a second to write this down. Okay, piecewise functions tend to kind of intimidate people, but what we really want to focus on is we are looking to find the integral, or the area under the curve, from -1 to 4 of f of x. But f of x is defined in 3 separate pieces. Now it's defined from -1 to 0, which notice our lower bound is -1. And then it's defined exactly at x equals 2. And then it's defined from 0 all the way to 4. Now, you don't need a graph to do this problem, but I want to just provide the graph visually for you. You don't need to write this down. But our goal is to find the area under the curve from -1 to 4, right? But this area is kind of oddly divided. So I need to find the area of this piece first. Let's do that in red. I need to find this area, which goes from -1 to 0, and f of x is a special function for that piece. So watch how our properties of integrals help us evaluate this function. Now it is important to practice proper notation. So what do I want? I want the full area from -1 to 4. However, I can't do that in just one piece. I have to use the bounds or the domain that's given. So I'm going to find the area under the curve from -1 to 0 of f of x, but in this specific piece of the function, f of x is e to the x dx. Okay? And then I'm going to add the second piece, which needs to go from 0 all the way to 4. And why do I know that it goes from 0 to 4? Look at the domain of the second linear piece. That's the area under the curve from 0 all the way to 4. Now we could do this, at least this part, we could do geometrically, right? This is just a trapezoid because that's a linear equation. But I want to practice our antiderivatives. So I'm going to put f of x, which now for this piece from 0 to 4 is x plus 2 dx. Now you might be thinking, well, wait a minute, what did we do with the exact value at x equals 2? Well, if I'm only thinking of this as linear model, the area under the curve, this little sliver doesn't have an area under the curve, or if I really wanted to, I could split this up and I could put a 2 to 2 f of x piece in here, dx. I'm going to erase this, so don't. But what is the area under the curve from 2 to 2? It's always 0, right? So that's why we don't put it, because that would just give me a line here. And if you wanted to, you could even split this up to go from 0 to 2, and then you have another one with the same function from 2 to 4, and that would split this up into 2 trapezoids. But we can kind of ignore one single point because that doesn't give us any area here. So I'm going to erase that because we don't really need that, but that is another property that pops in. So now the true area under the curve will be represented by the answer to these two integrals. And yes, you could do this in your calculator because they don't tell us to use our calculator or not, but I want to practice the no calculator work here. So let's just find the antiderivative of the red part. So whose derivative gives me e to the x? It's e to the x. Notice I'm not putting the integral symbol in there because I took the antiderivative, and now I'm going to evaluate it from the upper bound minus the lower bound. So we're going to plug in 0, and we're going to subtract the lower bound. Plug in -1. Now this is something that I think happened on the quiz. E to the 0. Remember, e to the 0 is 1. And then I can't really rewrite this other than calling it 1 over e. But e to the -1 is 1 over e. So that's the area under this red portion of the graph. And then we're going to add the antiderivative of the blue segment. So now I got to think whose derivative gives me x. Well, that would have to be 1/2 x squared, because if there's already a 1 here, and then I add 1 to the exponent, I'll put a 2. But if I put a 2 up top, I got to multiply by the reciprocal 1/2. Okay, and then whose derivative gives me just the +2, and that's x. Notice I did not put the integral symbol in front, and we're going to go from 4 to 0. And now I have my antiderivative. I'm going to evaluate it at 4 first. And I'm a big fan of just kind of thinking of this in terms of brackets. And then I'm going to plug in 0. But I know if I do 0 squared and 0 times 2, that whole piece is going to give me 0. So I don't actually have to show the 0 being plugged in if I'm confident that that answer is going to be 0. Now let's simplify. So we get 16. Half of 16 is 8. 8 plus 8 minus 0 is 16. And then I can take 1 plus 16 is 17. And I cannot add a -1 over e. So we're just going to leave our answer like that. And it's always a good idea at the very end to say what you just did. I just found the area under the curve from -1 to 4 of f of x dx. And my answer was 17 minus 1 over e. Write this part down here. So quick reminder, what does the fundamental theorem of calculus part 1 tell us? It tells us that an integral and a derivative are inverse operations. They reduce each other out. So that's going to come into play here, but we do need a graph, just a rough sketch. And I understand this isn't the most clear picture. So as you're writing this down, and then if we create a very rough sketch, I'm going to just label the important points on this graph so you can see them a little better. So there's a couple important things to really make sure you read a problem like this carefully. And I haven't even given you the problem yet, but let's look at what we have. So what is g? G is going to be the integral from -1 to x of f of t dt. Well, another way to think of that is g is the area underneath the curve of this graph. So they tell us twice, they tell us in the directions above, the graph of y is f of t given below. So this is the graph of f of t, and then your job is to understand that g is the area underneath that curve. G of x is the area under the graph of f of t. Okay, that's what they're assuming you know by that symbol. So my first question is, given this graph, knowing where our lower bound is, what is g of 2? And one of the things that I noticed in a problem like this is sometimes students try to do too much in their head, and they maybe make this problem harder than it needs to be. So what is this? This is saying, what is g of 2? Well, let's plug 2 into x. So anywhere I see an x, we're now going to go ahead and evaluate. Well, I know I go from -1 to x, but this time x is 2. And they're just asking me to find what is the area underneath the curve from -1 to 2. So where's -1? Right here. Where's 2? Right here. This area underneath this curve represents g of 2. Well, this is just a kind of a funky looking trapezoid, or you could split it up and do a rectangle and a triangle. I don't care how you do it, but I'm going to do the area formula of a trapezoid. So base 1 is, we can just count 1, 2, 3. Base 2 is the distance here. Those are the parallel bases, so that's the length of 1. So I would do 3 plus 1. And then the height, how tall is it between the bases? I just went up 2. And add those up, you get 4 times 8 cut in half. G of 2 is equal to 4. Now, that's kind of, I hope you'd feel comfortable with that, because that's not where these problems get really challenging. The challenging part is now, what if I ask you questions about the function g? Okay, and this is where the fundamental theorem of calculus really comes into play. So, where is g increasing? Well, we've learned something about that word increasing dealing with derivatives. So if g is increasing, that means that the derivative of g has to be greater than 0 when the original function is increasing. Okay, well, what does that mean? I need to take the derivative of g. Okay, now, I'm going to erase this part here because we understand that that is the area under the curve. So what would happen then if I wanted to find g prime? Well, I'm going to take the derivative of both sides. And this goes right back to the fundamental theorem of calculus that we did the other day. The derivative dx, d over dx, and the integral symbol, those are going to reduce out, and all we do is take this x and put it right into the function. And then remember, the -1 is a constant here, and its derivative is not going to come out. So what does that mean? That means that this is the graph of f of t, which t is a dummy variable, so if I say f of x, it's the same thing. So the derivative of g is also the graph of f. So the graph that we have is also the graph of g prime. Now here's the important part. You would have to show this. Okay? If you don't show this part right here, that you know that g prime is the f, you would not get full credit for determining this answer. Okay, well, now that I know what I'm looking at, I'm going to answer this. When is g prime greater than 0? Well, this is the graph of g prime, so when am I greater than 0? Anytime this graph is above the x-axis, that's when g prime of x is greater than 0. So I know from -1 to 3, all of that is above the x-axis. So my answer here is g is increasing on the interval -1 to 3. And my reason is right here, because the derivative is greater than 0. If you wanted a better explanation, you could write this. Since we know that g prime is equal to f, that's what we made a comment right here. So if I didn't have this here, I would have to write it here. So since g prime is equal to f of x, and g prime is greater than 0, then that's why g is increasing from -1 to 3, because we're above the x-axis. So you do have to make a connection to what your graph is with regards to the function g. Okay. We have 2 more questions that we can potentially answer here. Where does g have critical values? So now I'm thinking, well, what do I know about a function g if I want it to have critical points or critical values? So g has critical values anytime g prime is equal to 0. Well, we already made the connection in the previous problem that g prime is the graph of f, and this is the graph. So all I'm looking at is when does this graph equal 0? Here, right here, right here, and right here. I have 3 spots, or 4 spots, when g prime is equal to 0. And my reason why is right there, because the derivative is 0 for any critical values. Okay, and then the last one, let's see what color is going to appear best. Maybe a light blue. When do I have, or when does g have maximum values? Well, what do we have to know about g to find a maximum value? We have to know that the derivative is equal to 0, which notice we already answered that above, so one of these answers, or maybe more, is going to be my max value. So g prime is equal to 0, and there's a sign change, right? And we have g prime of x changes signs. If I'm going at a max, I go from increasing slopes to decreasing slopes. So my derivative goes from positive to negative. And you just say positive. If you want, you could draw a sign chart for this and just look at the fact that I'm negative here. So I'm negative and then positive, and then I go from positive to negative here, and then I'm at negative, but there's no sign change at the ends. So if here I go from decreasing to increasing, that would be a minimum value at -1. But at 3, I go from a positive g prime to a negative g prime. So I know that there would have to be a max. So there is a max at x equals 3. And then my reason is right here. So notice how I actually am writing the reason first. In my interpretation of this, I have to think about what does the word maximum value or what does the word critical value mean with respect to the derivative. And I write that out, and then I look for that on the graph. So I think writing your reason first and then using that to make a conclusion is a great way to approach these problems. So the important thing to note on these 3 problems is we could not have solved these 3 problems until we made this connection right here. We had to figure out how did G relate to the graph that was given, right? And it was the derivative of G was f of x. So that told us that this graph was the graph of G prime. Okay, so your homework tonight is going to be a couple of problems like this. And I want to just show you a couple of these quickly. Most of these slides you're not going to write down. I kind of want to show you just visually what could we have done to do this a little bit. So this is the same problem. It's a blurry graph, I apologize. But we have the area under the curve from -1 to x. And if I asked you to just figure out, well, what is the value of each one of those? Here's a table. And notice just quickly, if I asked you to plug in -3, you would go g of -3 is equal to -1 to -3 of f of t dt, right? That's what this part is saying. And then notice the bounds are flipped. So I actually could apply -1 is greater than -3. So what I'd want to do is I'd want to flip those and then make whatever that answer is the opposite sign. So by flipping them, that tells me to start at -3 and go to -1 and find the area underneath this curve, which we know is a base of 2 and a height of 1. So 1/2 2 times 1, but then it would be negative, and my answer would be the height is -1. So it would be a negative of a -1, which tells me the answer is +1. So this would be considered to have a positive area, and the only reason why is because we started at -1 and we went the opposite direction. So knowing that those bounds should be flipped is why we had the opposite value. Okay, so what if I just kind of did this and I took the area at -2. So I found the area from -2 to 1. Now notice its bounds would be flipped and it's half the value of this one, so its answer would be positive 0.5. Now what if I found the area from -1 to -1? Right? So if I plug -1 in here, I'm not moving left to right, so that has a 0 area. And then as I go to the right, you can see the area from -1 to 1. Well, that's positive 1/2. And then I could find the area at 1, at 2, and at 3. So notice, these are the values of the area underneath the curve. So what would be the integral from -1 to 3? It would be 5 total units. So if you found the area of this trapezoid, the answer would be 5. Well, what if I kept going? Notice it just keeps going down, down, and down. Well, we asked you the question, what was the maximum area underneath the curve? So notice, when x was equal to 3, I had a max value. It's the highest output, and that's area under the curve. So we know that my max occurred at x equals 3. Now, the reason why I'm showing you all of this is, well, these are points now, right? So what if I graphed G? Keep in mind, this is the graph of f of x, which is also the graph of G prime. So what does the graph of G look like? Well, I could just plot those points, and here's the graph of G. So notice, there's our maximum. Right? Our max is at x equals 3. That's what we found. When is G increasing? So when does it have increasing slopes? Our answer was from -1 to 3. And see how G is going up? So when is it decreasing? We could have found that as well. But that's just a visual connection to what we're doing. And hopefully you're just making a strong connection as we can answer all of these questions if we know the derivative of G. Okay, so that was a connection, but let me show you what you're going to be working with here today. It's up to you if you want to write this one. I don't think it's worth it because you would have to draw the graph, and it's a fairly quick problem. But let me show you how this works. And at any point, please make sure if you have a question, stop and ask. Just put it in the chat or unmute yourself and let me know. Okay, the function G is shown below. Now notice, that's the graph of G, and G is right here. So F is the area under the curve. That's what I know, that if I found the area underneath these curves, that's what F is. But then they're asking me to find F double prime. So I need to take the derivative of this piece twice. So I have to find the derivative. So if I take the derivative of F, that's just F prime. And then I know that if I'm taking the derivative of the derivative and integral go away, and that value x just goes in here. Now officially, because I should times by the derivative of this, that's that chain rule we talked about the other day, so I should times by 1 because the derivative of x is 1, but that doesn't change it, so I'm going to leave it just as g of x. Well, now I need to take the derivative of this again, so I need to take the second derivative of f, which is really the derivative of g. Okay? Now, if I was doing this as a question, I need to indicate both of what I just did. That's how you know the connection. So then, my final answer here is, what is f double prime at -3? Well, f double prime at -3 is equal to g prime at 3. What does that mean? That means we need to find the slope at x equals 3 of the graph g of x. Right? That's what this is referring to. So go over to 3. Here's when x is equal to 3. I need to figure out what's the slope of this line. And it's just rise over run. Up 2 over 1. Up 2 over 1, it's linear. So the slope is equal to 2. And since the slope is equal to 2, that means g prime, because this is the graph of g, so g prime is the slopes. And my conclusion is f double prime at -3 is equal to 2. Okay? We couldn't have made any of these conclusions until we figured out how f and g were related. Okay? And it dealt with the derivatives. So let's try another example. I don't think you need to write this down. Again, my goal is to just get you exposure to the types of problems. You can kind of tell they're all going to be on Delta Math tonight, which is good because you're given feedback as you work through it. So the function f is shown below. So, all right, here's the graph of f. G is given by g of x equals the integral from -6x of f of t. Well, what does that mean? G is the area underneath the curve. Okay, well, let's find that. Because they want me to determine the sign value of g of 3. Well, if g of 3, all I'm going to do is plug in a 3 here. So if I start at -6, Where's negative 6? Here's negative 6. So I'm going to start here, and I'm going to go to 3. All right, well, G is the area under the curve. So that's this piece plus this piece. Okay, area under the curve. Well, they're not looking for a specific number. This would be a value. Well, notice I have more positive area than I do negative. So G of 3, we know for sure, because it's going to be more positive area than not, that this answer is positive. Okay. Now, I have to figure out what is G prime of 3. But before I can figure that out, I need to figure out how does G prime relate to this graph that I'm looking at. So I need to find the derivative of both sides. Okay, so if I take the derivative of G, I get G prime. If I take the derivative of the integral, they reduce out, and I just plug the x in here. So that tells me that this graph of f is also the graph of G prime, which means G prime at 3 is really equal to f of 3. So that's a point. Whenever I go, oops, you know what, I made a tiny mistake. I went to negative 3 when I was talking about this. This might be wrong. It wouldn't be right if I didn't make a mistake, right? This is positive 3. So let me go back to the area under the curve. So I'm going from negative 6 to 3. And notice that adds all of this extra negative area in. So I've got negative area that's larger than the positive. So this should be a negative area overall. For some reason in my head, I thought it was negative 3. So I know that G of 3 is negative. G prime of 3 is the location. Right? Where is f of 3? So if I go over 3, where's my value? This value is 0. So I know that G of 3 is just a location on the graph because I know how f and G are related. And then the last part is, let's do this in green. I have to figure out what is G double prime. So then my question would be, if I take the derivative again, G double prime is actually the slope of f. So what I need to do then is I need to say, okay, G double prime at 3 is the same as f prime of 3. So I'm going to go to 3 and I'm going to ask myself, what is the slope of this line? And since it's a maximum, that slope is 0. Now I was able to tell what G was originally, what its derivative is, and what the second derivative is. And it all was due to the fundamental theorem of calculus. Okay. All right. What else do we got? We got a couple more that I think, again, I don't know if you want to write these down, but let's see. The graph of f is shown in the figure. Cool. Graph of f consists of a line segment, semicircles. Let G be given by this notation. That's the area underneath the curve. And they're asking me, when is G concave down? So what I need to figure out is that word concave down. Notice this is all a review from last trimester. What do we know about G when something is concave down? Well, the second derivative has to be negative. So that tells me I need to figure out what is the second derivative of G. Okay. Now, chain of command here, basically. We know what regular G is, right? G is the area under the curve. So what if I take the derivative of that? Well, the derivative and the integral are going to go away. So this x would just be put right in there. And I know that g prime is actually f. So this graph is also the graph of the derivative. Well then, what if I take the derivative again? So I get g double prime. That is equal to the slopes of this graph. So I want to figure out when is g double prime negative. When do I have negative slopes here? If I know how it's related, I'm going to check for decreasing slopes. So I'm increasing, decreasing, there's negative slope here, increasing, increasing, decreasing, and then increasing. So I have two spots, and those are the intervals at which g double prime is negative, so therefore the original function g is concave down. So if I was going to answer this as a free response question, my response would be g is concave down on the interval from -7 to -5, and from 2 to 5. And then my reason is because g double prime, which you should always relate to the graph of f, so g double prime, which is equal to f prime of x, is negative. Okay? Because we know concave down, the second derivative is negative, and that's what we're referring to here. Okay? So hopefully this is going to build your understanding of what we did in the past. Let's do this one as well. And again, it's the same thing. Here's the graph of f. G is the area under the curve. Now I have to write the equation of a tangent line. We haven't done this in a while. Well, to write the equation of the tangent line, I need point and I need slope. Well, the point is 0, comma something, right? So I need to find what is g of 0. That's the point. Well, that's just plugging in 0 here and here. And we know that that is the area underneath the curve of this function. So I'm going to start at -9. I'm going to find the area under this curve, and then I'm going to go all the way to 0. Now, to find the area under that curve, I'm going to split this up a little uniquely. You can do it however you want, but I've kind of got to find the area of these pieces and add them all together. So I know this is a rectangle, 1, 2, it's a 2 by 1, 2, 3, 4, 5, 6. So a 2 by 6, which tells me there's -12 area units down there. This is 1, 2, 3, 4, 5, 6 by 2. So 1/2 6 by -2 gives me a negative area of -6 under here. This triangle is a 1 by 2, so 1/2 1 times 2. This little piece is -1. And then we do have this extra piece that's a 2 by 1, 2, 3, 4. So 2 times 4 is 8, cut in half. Tells me that's a +4. So then I would just add all this up. -12, -6, that's -18, -1, -19, plus the +4. And that would tell me that the point g of 0 is -15. That's my x1, y1. But then I need the slope. And the tricky part is what is the slope? Well, the slope is the derivative. So I have to take the derivative of each one of these, but we know that the derivative of the integral is just going to reduce itself out, and that's the relationship. This is also the graph of g prime. So the slope that I'm looking for is what is the slope at 0, because that's where we're focused on. So when I go over here, I'm thinking, what is the slope at x equals 0? And this is a very interesting one. This slope does not exist because the slope on the left and the slope on the right is not accurate. So that means that the slope is undefined, which means I'm going to have a vertical line. So this one is a little trickier than we wanted to get to. But if the slope is undefined, then all it is a vertical line at whatever your x value is. So the tangent line at x equals 0 would be a vertical line because the slope is undefined, and that vertical line would have the equation of x equals 0, because that's the dotted line. Now notice it doesn't show this on here because this officially is the graph of the derivative, but that's kind of where we're at. So this one's just a little bit trickier. Okay. I might hold off on this one. That's a good one though. What I'd like to do is I want to show you how to do some of these in your calculator. So grab your calculator right now. And I'm going to make one up. I'm going to say, I want you to evaluate from -1 to 5 of 3e to the x plus 7x squared minus 4 dx. Okay? And we're doing this in our calculator. I don't want you to do this by hand. So if you had a question on, sorry, let me go back to this. If you had a question on how to do this from the video, I'll show you really quick. Now I will mention that you need a TI-84 to get this exactly the way it should look, and the video goes over it. So please watch that. But all you do is hit the math button, and then you go down to option 9. This is finite integral. Okay, so the INT stands for the integral symbol. Now, if you have the correct mode, it's going to look exactly like this. The video talks about what if you don't have this, and we'll share with that in a second. But all you do is type in the lower bound, the upper bound, and then type in your function, 3e to the x minus 7x squared minus 4. And then we always have to put dx. It doesn't matter if you have t's or anything like that, r's, h's. When we plug it in our computer or calculator, it's always going to be x's. And then hit enter, and there you go. There's your answer. Super quick. Now, if we ask you to show your work, then you're going to have to show this by hand, because you could do this one by hand and you get the same answer. Okay, so just be able to do both. We'll spend more time next week doing stuff in our calculator just so you're comfortable with it. If you didn't get this notation to pop up, watch the video, and if it still doesn't work, then we can talk. Some calculators, like the TI-83s, they don't have this notation, so you would have to enter it in differently. Okay, So we're going to skip this one. We'll do it next week. Homework tonight is a delta math. It's called 6-4 Day 1, Fundamental Theorem of Calculus Part 1, and Properties of Definite Integrals. That's the title of it. I'll be available from 1 to 2 in my office hours if you have questions. And do remember, you can do quiz corrections as well. Do them on a separate sheet. Take a picture of it. And you're only doing the ones you get wrong. And then email it directly to me, and you'll get 100% on the quiz. Adios. Have a good day. Enjoy the weekend.